In fact, now.
Yes.
Yes.
Yeah.
Right. So Tristan, it's a very great pleasure that you joined us today for colloquium, and it's then even a more even greater pleasure to introduce you. And I figured I haven't actually to say too much, except to refer to the fact that you are awarded the Rancorn-Florensky Medal from the European Geophysics Union. And they added a very, very clear description of your merits, which I simply read out because I think they really tell it all. So you will receive, in a couple of weeks. When is the EGU? In 3 weeks' time? 2 weeks' time? The Rancorn-Florensky Medal for your fundamental contributions to the study of the formation, interior, and atmospheres of giant planets and exoplanets, and for your inspirational leadership across multiple fields in planetary science. I mean, this sounds pretty impressive. Of course, we knew about it, but having it summarized this way, so congratulations for receiving that medal. I mean, it's coming your way in a couple of weeks, but the EGU is already advertising it. So, and of course, now we are very, very curious to see what you have to tell us in your beautiful talk. So, whenever you're ready, take it away.
Well, thanks a lot, Christian. Yeah, I hadn't seen what they were saying, so it's nice to hear. And yeah, indeed, I'm to receive that medal at the EGU, so it's a great honor, a great pleasure. And today, I want to talk about our results on Jupiter with the Juno mission and how it has or it's changing our view of the planet itself. And so it's going to be a little bit broad with quite a lot of nice pictures. That's the great thing when you have a mission to planets in our solar system. You can actually see what you're studying, and have great surprises, as you can see in the background here. So I want to first I want to say I'm sorry I couldn't be there with you. I would have really liked to chat more and visit the institute, but really it was too much for me. And of course we have to think about the planet also, and reduce traveling. So, but it's unfortunate. I would have preferred very much to be there. Okay, so what do we know about Jupiter? That's a picture that's very nice. Don't remember whether it's from Cassini, Galileo, probably Cassini on its way, I'm not sure. But that's pre-Juno, and we know Jupiter is and we've known that Jupiter is a very active planet with lots of clouds, with its moons, of course, and it's a very important object in the solar system, and to understand a giant planet as a whole. Jupiter is very active. This is a nice animation I like to show. It's not from spacecraft. Amazingly, it's been built by Peter Rosen from amateur images from the Earth. It can be a little bit misleading because it seems that Jupiter's winds are much faster than they are. It's in fact a stroboscopic image. So Jupiter as a whole is rotating much faster than that. And differential rotation is 1 to 2% of the main rotation, but still it shows that there's a lot of activity and there's differential rotation that is not negligible at all. So why do we want to study Jupiter? What are the main questions? Well, we want, of course, to know what Jupiter is made of. I mean, that's the main objective behind many of these missions, and in particular, the Juno mission. Jupiter is 300 times the mass of the Earth, so it's a major player in the solar system, and we still don't know what its main composition is. So that's, you know, it could contain, well, now we've reduced a little bit the uncertainty, but it's between 15 or 20 Earth masses to 30, 40. So that's a huge uncertainty to understand planet formation. We also want to know whether it has a central core, what its structure is, and things like that. We wanted also to know, and that's an area, as we will see, where we've made quite a bit of progress, how a giant planet rotates. It's not obvious at all because those are fluid planets, so there's no surface, and they're generally fast rotators. Jupiter rotates as Saturn does. For Uranus, Neptune, it's about 17 hours. And so there's a lot of angular momentum in there. And as we can see, there's these zonal winds, and we didn't know prior to Juno whether this rotation was deep or shallow. We want to understand, of course, the dynamics of these atmosphere and planets. They're very different from the Earth because there's no surface. There's also the property that all condensates are heavier than the surrounding gas because you have a hydrogen and helium atmosphere. So it can change things quite a bit. And I think that's what we're discovering at the moment. And then another very important question is what powers Jupiter's intense magnetic field. So we believe it has to be convective in the interior. So there's a very strong dynamo. You know that Jupiter has the most important magnetic field after the Sun in the solar system. And we need to understand all its complexity in order to apply that to other planets. So a very important characteristics of Jupiter and the other giant planets, except maybe Uranus, but even in the case of Uranus, I think, is that they emit more energy than they receive from the Sun. This is something that's been known since the 1960s, actually. And that led to the modern thinking of giant planets as warm objects with a cold atmosphere. You can see the temperature profiles in this figure. So you have pressure going, when you go down, you go into the planet, okay, on the y-axis, and temperature. Jupiter, of course, is the hottest of the 4 giant planets. So it's relatively cold. You're talking about 150 kelvins, something like that. 160 around the 1 bar level. And then as you go deeper, you're warmer and warmer. And this is because the planet is still warm from its formation, from all the energy that was transformed from potential gravitational energy, and it's releasing it slowly. So you can estimate that Jupiter is cooling by 1 Kelvin per million year presently. I mean, the interior of the planet is cooling at that rate. So there is a flux that can be measured. And I want to point out here that there's been an important revision of that flux by Liming Li, was published in 2018. So the flux has gone up from about 5.4 watts per meter square to 7.5, and the albedo that was estimated from the Voyager measurements essentially has been revised as well. So this is something to consider. Something important that I want to stress, and that is not necessarily so well known, is that that was a surprise from the 70s when the first pioneer missions went and looked at Jupiter, and it's that the temperature of the planet is remarkably uniform from equator to pole, and this is the red. I mean, those are heat fluxes actually, but if you look at the heat flux from the red curve here, it's very flat, and contrary to the emission. That's something that's, of course, to the received power from the sun, which is very low at the poles. Obviously, Jupiter is not very tilted, and high at the equator. So there's a strong redistribution of the energy that takes place in the planet, and this was something that was studied early on. And so there's three possible explanations for that. Either you have mixing directly in the atmosphere that's been proposed by Conrad and Girash, or there's thermal gradients at depth that counterbalance latitudinal insolation gradients. And basically, Jupiter is a very efficient conductor, and then you can't have very strong horizontal gradients. Poor co-explanation, and then there's this model by Ornu et al. Showing that deep convection can also generate a heat flux that is stronger at the poles and weaker at the equator to balance the insolation variation. But this is something that is key for us because it justified early on using 1D models for to model this planet, because the temperature is the same at the pole and at the equator. You can use the same equations and actually study the planet as a star. As for the sun also has a very uniform temperature in the photosphere. So it simplifies things a lot. But we'll see, we'll come back a little bit on that. An important thing to realize also is that because they have all this energy, largely convective. That was shown by Bill Hubbard in 1968. Dave Stevenson also studied that in the 70s. So the idea then is that the heat can be transported with a very small superadiabaticity. So it really simplifies the problem. So you can have an outer boundary condition that's the same at the pole and at the equator, and then an adiabatic structure inside, and all the way to the center. Okay, so you can see the superadiabaticity calculated with the mixing length theory is of the order of 10⁻⁵ to 10⁻11, so very small. The velocities from mixing length theories, again, are of the order of meters per second to centimeters per second down deep. The Rossby numbers are small, so it means that rotation will be important for convection. And this is a plot, again, from the Jupiter book, from some calculations I did a long time ago, showing that you could have some radiative zone deep inside, I mean, at a few kilobars in the planet. But if you account for alkali metals, generally you tend to block that opacity window, and you should have a structure that's indeed completely convective. Okay, those are all calculations that should be redone. Really, we have a lot more information than I had at the time. Those calculations had to be really simplified. Okay, clouds, and again, this is from old models. This is what we thought of clouds in Jupiter and Saturn. So as you go down in the atmosphere, you encounter an NH3 ice cloud, and then you have NH4SH that can form, and H2O. And then deep down, you can have an H2O and H3 aqueous solution. So the pressures are on the right side here. So you have pressures of a few bars, and basically the photosphere is at a fraction of a bar. So what you're seeing is around these. And actually, I think that you can see some NH3 ice clouds, but for some reason, they don't last very long. And maybe you're seeing more NH4SH clouds. And from time to time, you have windows in the atmosphere, and you can almost see H2O directly. So the Galileo probe was sent in 1995, and so that's what we expected. But, what was found was very little clouds, so a very dry environment in that region. And it turned out that the probe, by pure chance, fell into a very peculiar location, which is called a hotspot. So it's a clearing in the clouds. And this is something that we can see now with Juno. We have nice pictures of hotspots, and that was the explanation for the fact that there was very little clouds, but also very little water. So the water abundance that was measured by the Galileo probe was unexpectedly low. So Adam Showman and Tim Dowling had this explanation that locally you have a downdraft, so you can desiccate the atmosphere from all your condensates. And they actually have a model that reproduces more or less the observations, but requires that you have a flow with a perturbation in gravity, so that you force a downwelling at that location, and then you have a dry environment. So unfortunately, we don't have measurements of in situ measurements at other locations to compare to the Galileo probe. So all in all, the picture prior to Juno for Jupiter and Saturn, which is kind of similar, was the following one in terms of the interior: a compact core at the center, then a metallic envelope, well, with metallic hydrogen that's enriched in helium, and a molecular. Sorry, was there a question or? Okay. And a molecular envelope that has less helium, and a region in which you have helium rain. But basically, all these regions were thought to be homogeneous because of convection. Okay, the planet being so active, the idea was that everything should be relatively well mixed. Okay. So Juno was launched in 2011 and arrived at Jupiter in 2016. And you see it's a big spacecraft, solar powered. It's the particularity here was to study mostly Jupiter. So it's been designed, all the instruments have been chosen to be able to study Jupiter and Jupiter's interior rather than the system itself. We had, the idea was to have an initial 53-day orbit and then to 11 days, but then there was an issue with the thrusters, and they decided it was too risky, so we stayed with the 53-day orbits. And actually, it's been very, very good for the mission because it allowed longer exploration of the system, the possibility to go also further away in the magnetosphere. So in the end, it was a good event that we couldn't shorten the orbit. And NASA extended the mission to 2025. So the orbit is precessing. So instead of being closest to the equator, we're closest to the northern latitudes now, and so we're going to be able to study the northern regions more and more accurately in the future. Okay, a particularity of Juno is that you get very close to the planet. You're only 4,000 kilometers from the cloud tops, avoiding the Io plasma torus. It's becoming more of a problem at the end of the mission because of the precession of the orbit. But so far, the spacecraft is in nominal condition. We had one slight problem at the last perijove, but things are going very well. Yes, and so this particular orbit allows you to have a very good accuracy on the measurement of the position of the spacecraft and thus on the gravity field of the spacecraft. So this is Juno. You see it's a big spacecraft with this suite of instruments. What we're going to be interested in is mostly the gravity science experiment. And so this is just the radio antenna that relays to Earth, but that is deflected by Jupiter's gravity. And then the MWR instrument that probes the deep atmosphere, and a small camera in the visible, that's JunoCam, that's used for the visible images. So that was one of the early pictures. It's a montage actually of Juno, or maybe it's not actually this one. Yeah, it's when it was leaving the South Pole, and it was the first time that we could see the poles of Jupiter, because all the spacecraft before that had been in the equator of the planet, so we didn't have a look at the poles. You can see that the color changes, and it's believed that there's less absorption at polar latitudes, so you have more scattering, so it's more blue in color. Although these images are often their contrasts are strongly enhanced. It makes them more spectacular in a way, but there's also a lot of information there that you can see more readily thanks to that. So we can see all the structure of storms and vortices in this planet. And I'm going to show a few of these because they're beautiful and also instructive. You can see that really there's a lot of turbulence with these anticyclones over there, and then we have clouds that lie above the rest, and we can I don't know if you can see that, but there are little shadows. So really the sun is to the upper left, and so those are, I believe, ammonia clouds popping up higher than the rest of the cloud structure. So we have a lot of images like that. Those are at high latitudes, a lot of turbulence. And the colors sometimes, I mean, the change of color from one image to the next doesn't mean anything specific, but the change of color within one image is something that is real, and it reflects slightly different compositions and probably things that are brought from the deeper interior in a more or less important way. Okay, so let's go rapidly. So you see that there's a lot of activity on this image. You can feel that there's really different cloud layers, it seems, but there could be opacity variations. And then you have, yeah, this kind of image also. So a lot of structure, a lot of.
It looked like an oil painting to me. So like a Van Gogh painting, it doesn't look real. It like thick paint somehow.
Yeah, absolutely. It's and of course there's been a choice of in the processing of the image. The colors have been enhanced, but still you have all these structure is real, and you have these little clouds that are there, and those are real. So all this is still to be really understood. The colors, the meaning of all that is not fully well known. Okay, so let's now move to the study of the gravity signal. So the idea is that the spacecraft transmits a signal, it's Doppler shifted by the motion, and then because of perturbations of the gravity field, the motion of the spacecraft is not completely smooth, and so you can analyze that and get the gravity field of the planet in a very accurate way. And this is what is shown here with these gravitational moments. So J4 and J6, those are important for interior models. And you have three determinations that are prior to Juno, the Voyager one, and then there's been two reanalyses in 2003 and 2011, and you see that they were discrepant. And then on the first perijove, Juno found this value for J4 and J6, already something much more accurate. And this corresponded actually to models that had calculated Nadine Nettelman at the time. And then on the third perijove, we had an even more amazing accuracy. You see the little yellow square here, this is the measurement with the error bar. So can't even see the error bar anymore. So this is great, but then it's a problem for interior models because it became suddenly much harder to fit the measurements, and this is what we're gonna see. So there was a few papers. I'm going to go rapidly on that because I want to spend a bit of time on the atmosphere structure. But basically, early on, we realized that we generally needed to have a dilute core, so namely a core that's not well defined, but dissolves into the metallic hydrogen envelope in order to fit the gravitational moments more easily. And so this has been shown by Chenwall et al. And then by Debras and Chabrier, who really tried to fit the gravitational Juno's gravitational moments, and also including the constraints of the Galileo probe that the envelope should be relatively metal rich, about 3 times solar. But it's very hard to do because interior models tend to predict a structure of the outer, the molecular envelope that's poor in solids. Generally, we want to have a low density there. The equations of state have become higher density in the past years. And so it became really hard to find models that fit. So in that model, Debras and Chabrier imagined that the metallicity, the amount of heavy elements, can actually be high in the atmosphere and then decrease somewhere in the interior, in the hydrogen helium envelope, and then increase again when you have the dilute core. Whether this is possible physically, it's not completely clear because you have to stabilize all that. With Shamila Miguel, we did an exploration of a wide ensemble of possibilities with different equations of state to show that in any case, you do need to have an envelope that is inhomogeneous, and that's really a strong conclusion. So it means that when you're forming the planet, and because probably this has to be set up during formation, you need to accrete hydrogen, helium, and heavy elements at the same time. Recently, with my student, Saburo Howard, we also reanalyzed the properties of this dilute core using different equations of state. I'm going fast on that, but the idea is that in the Debras, Chabrier, and the Militzer et al. 2022 solution, we have dilute cores that are relatively extended. And this is not in line with predictions from formation and mixing models, which predict that the envelope should be relatively uniform, and only the inner 20% in mass could keep a gradient of composition. So in our solutions, we do have some of the models that actually agree with that. So on the left-hand side of these diagrams, but there's still work to be done. And one problem that remains is that when you want to do that and you don't want to have this negative heavy element gradient in the interior, you need to increase the temperature of the interior above the Galileo probe value. So above, to be either super adiabatic or have the entire planet being a little bit warmer than the Galileo probe value. So there's been a reanalysis of the Voyager data that points to higher temperatures, and that's been done by Gupta et al. and this goes in the right direction, but this is at some latitudes. The Galileo Pro value is something that is secure at that latitude, so it would point to an atmosphere that's not completely uniform, and where temperature varies by at least a few kelvins, and maybe it's not that surprising after all. So let's go back now to the issue of rotation. That was one of the big questions, and this is a field where we made great progress. So the question was, does Jupiter rotate, as a solid body mostly, and then this is just skin deep, this differential rotation we're seeing, or is the differential rotation penetrating quite deep in the interior on cylinders because of the low Rossby number and the Taylor-Proudman theorem? So that was a question that had been there for more than 40 years. So those are the zonal winds as a function of latitude. You see it reaches more than 100 meters per second. And this is the map of gravity anomalies that was measured by Juno. And you can see that you have anomalies and that you have an asymmetry between the northern hemisphere and the southern hemisphere. And in the zonal flow, you also have an asymmetry between the north and the south. So that's meant directly from seeing that Jupiter's gravity field being asymmetric, these flows had to go deep enough so to involve enough mass to be detectable. And the idea is that when you have a faster rotation, the centrifugal force changes your density. And you have actually a relation that's called the thermal wind equation that relates the gradient of velocity of zonal flow to the density that you will have in a particular region, or the density perturbation. From that density perturbation, you can calculate a gravity perturbation, that's this delta J. And that's been done by my colleague Johan Caspi, that predicted actually that you should have odd J's that could be detectable if the flow was deep enough. And that was exactly what was found by Juno. And amazingly, all the odd J's match more or less the predictions, both the sign and the amplitude, when you have a flow that extends to about 2,000, 3,000 kilometers. So that's the depth of this shell here. Okay, so you have to imagine that you have rotation on cylinders here, and then you have a decay of that rotation radially. So all that inside the white part is in rigid rotation. And what I did was to also calculate interior models and look at the even J's, where here you have a degeneracy between rotation and interior models, and it led to the same solution. So the idea is that you have a differential rotation, in this brown region. The planet, the hydrogen becomes convective. So then the flow is dragged into uniform rotation by the magnetic field, and the dynamo is created somewhere in the metallic region. Okay, so the picture we have for the interior of Jupiter, and also the other giant planets, is that one. Now it has changed. So we have this dilute core. So it means we probably have a lot of static stability there. We still have convection probably in large parts of the planet, probably. We need the dynamo anyway, and we need to transport this heat flux. We have this rainout region. In Saturn, Mankiewicz and Fuller, using seismology, found the same kind of phenomenon, but involving both helium and heavy elements. It's a very nice work. There's other things that point to static stability, stable regions. In fact, Wisht and Gastin found that it's hard to explain the decay of the zonal flow in that region. Even the conductivity is not high enough there. So maybe you need a stable region. And then a work that was done by Kimi Moore recently also points to stable regions to explain the particularities of the magnetic field. And then there's also two papers looking at the magnetic field using a statistical approach, showing that the dynamo core radius could be around 0.81. So it means that you'd be stable above that radius in order to explain the magnetic field that's observed. So maybe we have to move that layer of helium rain out a little bit up. That part that is not strongly conductive could still be convective without influencing the dynamo too much. Okay, so let's discuss a little bit measurements from the MWR, the microwave radiometer. So this is a set of antennas that probe the deep atmosphere. Those are weighting functions. The different antennas probe different regions. So you're going from a fraction of a bar to almost a kilobar. So that's your sensitivity. And thanks to that, we were able to see for the first time the deep atmosphere of the planet almost in 3D. And one of the storms that we saw is something like this barge here that's been observed by Juno Cam. It's not exactly the same, but and so those are the maps from MWR that as a function of latitude. So as you go from right to left, you're going down into the planet. The rightmost map here is a Hubble image at the same time, so in the visible. Then you have a near-infrared image from Gemini, I believe. And you can see that, I mean, you can see the features. And there's two features that are of importance. It's an anticyclone here and a cyclone. That's the barge that we saw in the previous slide over there. And you can see that the anticyclone persists as you're going down, but disappears after a while. The barge is here, it's bright, there it's bright, and then it becomes dark in the lowest channels, and we can see a little bit of it there. So we could analyze these structures in 3D and show that you have anticyclones that have a denser top, generally cold and dense, and a lighter bottom. And it's also the case of the Great Red Spot, and cyclones that are inverted as should be, with a warmer top that's lighter and a colder bottom that's denser. So this is something very interesting when studying the deep atmosphere. These structures go deep. They go deeper than the H2O condensation level that is here. much deeper than the NH3 one. And then the great red spot is the one that's extending the most. It's a big structure, it's very extended, so the atmosphere is perturbed till quite deep. So this points also to static stability. There was a study by Mike Wong that produced this nice diagram, and he showed the static stability that is used by different models of the atmosphere. So we need the atmosphere to be stable on average as well. So we shouldn't think of it as being fully convective. It's convective from time to time, it's active, but it's also stable. I'm going to go very rapidly on that. We had some measurement of on the great red spot. We had 2 passages over the great red spot, and we could detect, it's a very small signature. We're talking about here, it's micrometers per second. That's the accuracy we're getting on the measurements. It's something completely amazing. And so we have a signature of the great red spot that's modeled as a dipole like this. And it leads to a depth that's around 400 to 500 kilometers. So that's the structure of the great red spots. It's a pancake. Still 500 kilometers, it's quite deep for an atmosphere. You're very much deeper than the water condensation level there. So what we've been seeing is that in terms of ammonia abundance, we were perturbing the atmosphere until much deeper than expected. I've proposed that this is linked to the presence of storms and what we called mush balls. So the combination of ammonia and water that's able to form some hail-like particles that are able to go deep into the atmosphere. So the idea is that when you make this phase diagram, that's from an old paper by White and Schilling and Lewis. Those are the solid phases of H2O and NH3. So when you're going to the left, you're going to lower temperatures from higher temperatures to the right here. Those are the vertical lines. So at low pressures of NH3, so low abundances of NH3, you have at 0 Celsius the solidification of water. Okay, so that's okay. But ammonia is a very powerful antifreeze. So if you add ammonia, you can have a liquid ammonia water. And the concentration are the blue lines here. Okay, so all this is liquid. And Jupiter happens to lie in that region, given its ammonia abundance and its pressure temperature structure. So it means that if you have a water ice crystal that goes up from the deeper regions, it will solidify, and then it will cross that region where it can interact with NH3 vapor and form a liquid. And that's where we believe these mush balls can form. So it's really a liquid NH3 H2O component that forms. And what I did was to model in a very simple way. I mean, the idea is just to prove the feasibility of that you could grow particles like graupels and hail on Earth with that. So I'm not going to go through that and just show you the sketch. So the idea is that you grow as an ice crystal, and then you cross that region, then you liquefy, you're able, so you change the differential velocity of your growing particle compared to the others, and so it's able to grow until it's too large and cannot be lofted by the updraft, so it begins to it falls, and then you can rain out, and then you evaporate, and then you can still go down because you'll have downdrafts because you're cold and heavy. So this is a small animation that was prepared by NASA to show what may happen. So you form this mush ball of ammonia and water, and then it's capturing, as you're going down in the cloud, so you're capturing the water ice, so it grows. And then that's how you can transport this ammonia efficiently. Because the ammonia is at the core, this is the one that's evaporated last. So that's the idea behind this simple model. And we showed that actually there's a correlation between the lightning that we observe and the lack of ammonia that we see. So indeed, the regions where you have more storms and where you're able to form these mush balls more efficiently are the regions which are depleted in ammonia. And they should also be depleted in water. So it poses a question of the abundance of water globally in the planet. So what we found also was that we found a new kind of lightning. So because of one instrument from Juno, the star tracking unit. So those are very what we call shallow lightning, because the lightning flashes are very small. So it means they haven't been scattered by the atmosphere. They must originate from quite high in the atmosphere at temperatures that are below -66 Celsius. So it's a region where you can't have pure water that's a liquid. So interacting with the ammonia is key in order to build these large particles and have the charge exchange that you need to form the lightning. So you both have deep lightning and shallow lightning that's observed in Jupiter. There would be much to say about that, but I don't have time. And
I think we should slowly come to an end. So maybe
yes,
another 3 minutes or so.
Yes, that's those are my last slides. I just want to point out that there's a question of how deep these condensates go, and this is something we've been working with. Steve Markham, that's the postdoc with me here. So we've submitted a paper showing that when you have precipitation, it's heavy and it's cold, so it goes down. Goes down rapidly and quite deep to several hundred kilometers. That's what we need to explain the Juno measurements. And it's a global question, actually, in all planets with hydrogen atmospheres, for Jupiter, but mostly for Uranus, Neptune, and for exoplanets. You can have an inhibition of moist convection because of the fact that condensates are heavier than hydrogen and helium. So this is something to care about. I just point you to this paper by Steve recently on super Earth that could be much warmer than we generally expect because of this inhibition of convection. So this is something to study. And I want to finish with my last slide, which also shows the approach of Juno on Jupiter, asking the question, what's next? Well, we will explore Jupiter's northern hemisphere until 2025, so that's going to be tremendous. We will also have radio occultation. Several are expected already this year in September and next year. So that will give us information on the temperature as a function of latitude down to 0.5 bar or something like that. That's the expectation. So that's going to be really great. I'm really looking forward to that. JUICE will resume monitoring Jupiter's atmosphere even after Juno is gone from 2031. JUICE is focusing on the moons, but still we will have the capability to monitor the atmosphere, look at high resolution to storms and stuff like that, and see the long-term evolution of the planet. So that's something really interesting. What I'd really like to see is a Jupiter L1 observer that can do seismology. So you stare at Jupiter from the Lagrange point for 2 years, and then you can probe really the interior. And then we have the next frontier, which is Uranus. There's a flagship mission that's been decided by NASA and ESA is to contribute by building the probe. So I really look forward to that for the next generation, but it's going to be a tremendous mission. So I'll stop with that. Thank you.
Okay, we have time for a couple of questions. I also maybe look online. If somebody wants to ask a question from online, please raise your hand. Otherwise, maybe we start with questions from the audience.
I have one. Tristan, thank you for this very exciting talk. And you touched, of course, on many questions that we are also exploring here for exoplanets. I'm very curious to learn a little bit more what is actually, and this was your leading question, what is beneath the clouds? So can you give us maybe an educated guess? I mean, I saw your argument about the metallicity change. Can you maybe give us an educated guess how strongly the local chemistry in the atmosphere would change going inward?
How strongly the metallicity would change?
No, how the chemical composition of the atmosphere would change going deeper into the below the clouds.
Yes. So for ammonia, it changes from 100 ppm to about 350 ppm, down to tens of bars. So that's so you have changes that are both in depth and in latitude. In longitude we don't know exactly, but there will be changes as well. If you look at the more the bigger picture, more deeper inside, we need, in order to fit the gravitational moments more easily, we would really need this heavy element abundance to go down to something that's below solar at depth. I'm not sure it's realistic. We are considering that with Saburo and calculating models as we speak here, but to me it doesn't look very promising that this is the solution. I would favor rather some changes in the equations of state, or some changes from studying Jupiter as a 1D planet to a really 2D or 3D planet, which can change things quite a bit. But I don't know if I answered your question.
I was hoping more that you would talk about silicon and magnesium and iron and all this stuff. But clearly this is not entirely on the table right now.
Yes. Yes, for the more refractory elements, this is something that is a big question, and it's very hard to it's very hard to address because we have very little information. So we are working right now, and Cheng Li and his student are doing most of the work on alkali metals and the possibility of that radiative zone inside, and at the same time alkali metals are providing electrons, so they're important for the opacities in the microwave in channel 1 and channel 2 of the MWR instrument. And so we may have some indirect constraints through that, but otherwise what's very hard with giant planets in our solar system is to get constraints on things like iron and silicates and all these species. And so this is where, as you were alluding to, exoplanets and giant exoplanets and hot Jupiters are really interesting, because nature is giving us a tool to study what's happening at levels that are too deep in our own Jupiter. But around a hot Jupiter or very hot Jupiter, you can have iron that's in vapor form all the way to the photosphere. So if we could have some signatures of refractory species from that, that would be tremendous. So I'm really looking forward to the observations by JWST and hope we can get that.
Thank you,
Professor Guillot, may I ask you a question concerning the great red spot? Is it a permanent phenomenon, or is it temporary, and how deep does it reach? Could you explain something about that?
Yes, so I showed a little bit how deep it reaches. I'm going to show the little diagram again here. Well, this one is probably more clear. So I don't know if you can see here. Let's see. It's yeah, the depth is here from 0. That's the surface to about 400 kilometers. That's the constraints that we have from gravity. And from the MWR, we also have the same kind of determination of the depth of the Great Red Spot. So whether this is a permanent vortex or not, it's hard to say. People believe it's not permanent, because we see vortices come and go, and the Great Red Spot has changed a lot since Voyager times, but we know it's lasted for at least 300 years because we have drawings from Cassini. So I remember that after I did my PhD, and in the year 2000, there was someone presented a prediction that the Great Red Spot would disappear by 2020 because it had shrunk to something almost spherical that should be unstable. So obviously it hasn't disappeared, but we will see. So what we're seeing with Juno is that it is the vortex that has the deepest roots. So it's something, it's like a monster. So it should be able to persist still for some time, but how to predict that, no one knows really, because yeah, we don't yet have the ability to really model its evolution.
And does it appear on other gas planets too, or is it a singular phenomenon?
Other planets have vortices, but all of them have disappeared since we've observed. So there's none that has spot, I mean, a vortex that has long lived. When Voyager arrived at Neptune, there was a big spot that since has disappeared and changed to something else.
Thank you very much.
Yeah, so it's the only one.
Any other questions? There's some question from Maxim Kurachenko.
Yeah, thank you. As we can see, there is certain progress in understanding the interior structure of Jupiter, which is based on the measurements of gravitational disturbances and estimation of the momenta. At the same time, there is another phenomenon also measurable, which is sensitive to the internal structure. I mean, magnetic field, magnetic dynamo. My question is, to which extent the new data, the new imaginations regarding the internal structure of Jupiter are consistent with the dynamo models of Jupiter and comparable to the measurable magnetic field?
Yeah, thanks. That's a great question. There's some work on the dynamo that's taking into account what we know about the interior models now, and I alluded to that when presenting this figure. So that's the work by Kimi Moore, and she requires stable regions in order to fit the dynamo that's observed. Unfortunately, these simulations are not yet to a point at which we can be very assertive, because the models are still quite crude. It's very difficult to do. It's very difficult. We don't reach the right resolution. So there's an intrinsic problem of resolution, but we're progressing. So and we have also these other methods that study the dynamo, but from a statistical approach, using what we know on the Earth's dynamo. Actually, it appears that the Earth and Jupiter's dynamo have similarities, and when you study the decay of the moments of the magnetic field, you can reach a conclusion that the dynamo should be produced inside the radius that is in one study 0.81 R-Jup, in the other study 0.83. So we're getting some information, but we don't have the whole picture.
Yeah, at least it is not forgotten, which is good.
Yeah, absolutely.
Okay, good.
Yeah,
Thank you.
I think at this point, in the interest of time, we should finish the meeting for today. So thank you very much, Tristan, for giving this exciting talk. And thank the speaker again.
Well, thanks a lot. Thanks, everybody.